is it? You know where it is, right? Chapter 7, 7.8, improper integrals. So this is 11.3. And this is titled integral test. The integral test and estimates, that help us to do some sort of that. In addition to detecting whether a series is convergent or not in a certain cases, it also provides a way of estimating the sum. So, we first consider an example. So opening an example. Before I say that, I should point out one thing. Several of you asked me about some of the homework problems, and so I, in the course of helping them, I said more than once that pretty much the only test that you have learned so far is what is called the test for what? Divergence. Remember that? And so I said more than once that that test of divergence is pretty much very useless test when it comes to deciding, trying to prove that the test is convergent, because it offers no way for you to show that a series converges. That's why it's called a test for divergence. What it says is that if the individual terms doesn't converge to 0, for example, if it doesn't converge at all, or it converges to say 3, then forget it. The series, the sum thing, the formal sum, cannot possibly converge at all. It has to diverge. So stop investigating. That's what it says. Okay? So it's useful only for the most obvious case where a series diverges. So as soon as you see that the individual term doesn't go to 0, then stop. That's it. That series definitely is not convergent. That infinite sum definitely doesn't make sense. All right? And so that's the only place to use that one. This is pretty useless, pretty much. It never helps you to decide whether a series actually converges. If a series converges, you cannot cite that one to prove that the series converges. You can cite that one to show that the series diverges, but you cannot cite that one to show that the series converges. So here comes the problem. For example, compare 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus. This is called harmonic series. And compare this one with the next one, which is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus. In either case, that test of divergence says nothing. Right? Because the test divergence says that, if the individual terms doesn't go to 0, then stop. Right? The series must be divergent. Right? But how about if the terms does go to 0, as in this case and in that case? Then you say, well, I don't know. It could converge, it could diverge, it just don't know. So it's pretty much useless. Right? And so as it turns out, this one diverges, whereas this one converges. As it turns out, but not with the help of the test for divergence, of course, right? All right. Now, in general, you see the pattern here. This is denominator is 1, 2, 3, 4, 5, and this is first power. Is that right? Right. This is 1, 2, 3, 4, 5. raised to the second power. So in general, you could have 1 over, in general, you have 1 over 1 to the p's power, 1 plus 1 over 2 to the p's power. Right? So we call that the p series. So I'm going to write down later. But for now, let's just focus on these two examples. Now, what we are going to do is to make a connection with 7.8, which has to do with some proper integral. So I'm going to draw nicely a picture, or as nicely as I possibly can. Here's another one. Okay, I'm gonna use a different scale for x and y. Otherwise, it's kind of awkward. So here is 1, and so here is 1. And when 1, it is 1, right? And when it is 2, it's 1/2. When it is 3, it's 1/3. It's about here. When it is 4, it's 1/4. Oops. Here. Okay. But this is one of those cases where these values, these dots, happen to fall on some familiar curve. What is this curve?
1 over x.
Yeah, this one is y equal to 1 over x. And you just specialize x to these integers. Then you get this series. Right? Okay, so likewise, here is another one. Here is 1. It's 1, 2, 3, 4, 5. And here is at 1 is 1 over 1 squared, that's 1. 1 over 2 squared is 1 over 4, so it's over here. And it dropped very quickly, 1 over 9, 1 over 16, and so on. So it's dropped quite rapidly. All right. Now, when it comes to 7.8 improper integrals, we are being integral. We care about the areas under the curve, right? Okay. Now here we are not calculating the area whatsoever, but we can make a connection nevertheless. So what am I calculating? I can interpret this sum in two different ways. First way, can it be written as this, the sum of these areas? Do you agree? That's one way of doing it. All right? What is this one? That is 1 over 1 times 1, right? 1 over 2 times 2, 1 over 3 times 3. That's one way of doing it, correct? But there's another way of doing it. For example, this area represents pretty much A1. Right? But rather than drawing the first rectangle with that particular height and width 1 that way, may I turn this around and do this instead? Wouldn't that be the same? That would be the first term. A1. All right? And what is A2? Just different arrangement. Right? Sometimes you do the first way, sometimes you do the second way. Depends on what you're trying to achieve. Right? So here, for no particular reason, I'm going to turn it this way. And in a moment, you'll see why. Is that okay? So in summing this series, that is the same as summing the areas of all these rectangles. But the reason that I turned it this way as opposed to the first way that I drew is because of the following. If I do it this way, then would you agree that if you compare that with this part, oops, I shouldn't use this color. Let me thicken this one to use black. This curve here, would you agree that if you compare this this region that I have just drawn, this staircase starting here at 1, starting here, first rectangle, continue with second rectangle, and so on, right? Something like this. That is dominating this area. Would you agree? That's greater than this area. Do you know what I'm talking about? I mean, this area, if I remove all this, look at this step function, starting at 1. Go like this. And in asking, in doing the sum, this infinite sum, this series, I'm really calculating the area under this staircase. Is that right? And would you agree that that area is bigger than this shaded black area? Right? And now you understand why I make a choice of turning these, the staircase this way. And that is because I know one thing back in chapter 7. I know that this shaded region is nothing other than, so the shaded region is nothing other than integral from 1 to infinity, what I'm going to write. 1 over x dx. Is that right? And remember this one, I mean, you recall how formally this is supposed to be. This is 1 to capital L, right? And then you're going to take this one, and then x, and then evaluate at 1, evaluate at L, and then, you get ln L minus ln 1. ln 1 means 0, so ln L. And then you're going to let L, the right integration limit, approach infinity. And so this expression of ln L, when L approaches infinity, of course, it blows up, right? So what do you get? Yeah? So I know that this shaded area blows up. It's an infinite area. And yet this staircase, enclosed an area which is even bigger. So then, of course, that area blows up as well. That is to say that this one is infinity. Yeah, this sums to infinity. It keeps growing without bounds. And therefore, that series converges. Diverges. So this one diverges.